Hello and welcome back to Calculus 2. I forgot which one I'm in. So this is our last lecture, and it's titled, unfortunately, Chapter 12. I wish I had more time to do these three sections all separate, so we'll have to cram a little bit so we can also review for the final. So Chapter 12 is known as your Calculus 3, Introduction to Calc 3, and what you learn here is you learn two of the very important prerequisites, and that is parametric equations and polar coordinates. So this stuff is used a lot in Calc 3, and I'm really asking you during the break to go to the book, go to the MyMathLab, which will be available to you. I'm leaving it open, and practice Chapter 12 if you are going into Calc 3, because without parametric equations and polar coordinates you will be dead in the water eventually. Now let's see what these are. So 12.1, parametric equations. Your line integrals and many other things will depend on parametric equations. Now, parametric equations will take your regular equations that you know and love, y equal f of x, and they will separate the two dimensions, dimension of x and dimension of y, into separate equations in terms of the newly introduced parameter, say t. And that t could represent time, for instance. So here is the example, cheapest one you can possibly think of. If your f of x is, well, let's say y equals x squared. This is the good old parabola you all know and love. Now, this parabola is a two-dimensional creature because you get to graph this on a two-dimensional xy coordinate system, and clearly there is a dimension that you call x, and then there is a dimension that it's called y, and both of these dimensions are dimensions of length. So now what I'm going to do is I'm going to create a set of parametric equations where I will have equation for x and equation of y, and as a set those two equations will represent y equal x squared as well. So it's a different representation of the same function. That's all it is. So you have a single two-dimensional equation here. What we are going to do in parametric equation is write them in a separate dimension. So I'm going to introduce a parameter t, and if I replace x with t, then y becomes t squared. So can we actually show that this is the same? Sure, because your x is equal to t, just plug it here, you get your x squared, you're done, right? Parametric equations are not unique representations. So I can be creative if I need to. Another set would be x equals, let's say, square root of t, and y equals t to the fourth. This is also representation of y equals x squared, because if I plug in square root of t for t, square root of t to the fourth is t squared. So it is not unique. You can come up with many different ways in which you can make your equations work. Here is another example from, again, something that it's easier. Say y is equal to x plus 1 squared minus x, let's say, plus 3. Let's say this is something. What you can do for your parametric equation, you can say, you know what? I'm going to rewrite this using algebra. So x plus 1 squared. And I'll say minus x minus 1 and then plus 4. What I have done is I put minus 1 and plus 1 into the mix. And now I am going to factor this minus sign. And get another x plus 1 and then plus 4. So now, what is my parametric set? This is not unique. There are many ways and you can do this. I'm just tossing in whatever. So, it would be so nice if I just had t squared minus t plus 4. Right? That's what I was aiming for. So now what goes here? T minus 1. T minus 1, right? Because you can clearly see that I define this as a t, right? So what's x? Right? If I define this as a t, then x is t minus 1. Now, this parametric set is generally much nicer to deal with than the original equation that you have. But we should all agree that all of the examples that I presented so far are completely pointless because your original equation was always much better than any of the stuff that I wrote, right? Because, hey, I have one equation that I can deal with. Okay, I am with you, and I agree. But now, we switch to the next example. No spice. Easy, straightforward. We are going to have an equation that says x equals 3 cosine t and y equal 3 sine t. These are nice and beautiful waves, right? We understand sine, we understand cosine. Can we differentiate these without thinking? Yep. Can we integrate these without thinking? Yeah. We can do anything. Compute them. Beautiful, right? What do these represent? What are these equations for? If you are to combine these together, what equation they're going to give us? Because if I combine these two together, they're going to give me this, right? If I combine these two together, they give me that. So what happens if I combine these guys? What do I get? Well, what you get is x squared plus y squared is equal to 9. You get a circle. Oh. Is circle a function? Is circle a function? Do you get to integrate? And what do you have to do to differentiate? Implicit differentiation, right? Not fun. Why? Circle is not a function. So all of a sudden these parametric equations look really sweet, right? Yeah, there are two of them, but they're both functions and they're both nice. That's what I did.
No, but I'm saying like you could just move it to the other side at this point. Just go with it.
You still get plus minus, yeah. But you have the square root, it's still nasty.
Oh,
Right? Would you rather take the derivative of a square root or a cosine?
that's true.
That is true, right? So, great. Now, you asked me how and why, right? Well, let's convert this real quick. So from the top equation, we're going from x equals 3 cosine theta, t. We will say that the cosine t, cotangent, cosine t is equal to x over 3. And then hit it with the inverse on both sides. T equal cosine inverse of x over 3, right? Now you plug that into the sine equation, and you get y equals 3 sine of cosine inverse of x over 3. Do you remember these problems from earlier in your life, when it was just an annoying thing for you to do without any reason why? There it is now, all right? Now, if you recall, the way to solve this is you draw the triangle, assign values, and then read the inverse sine. Cosine is what over what? Cosine is adjacent over hypotenuse. Good. So adjacent over hypotenuse. So now what's this puppy here? Well, that's going to be Pythagorean theorem of 9 minus x squared. Perfect. So now y equals 3 sine, and now I need sine inverse. Read the sine. That's going to be square root of 9 minus x squared divided by 3. The sines die, and what you have is y equals 3 times the square root of 9 minus x squared over 3. Well, 3 is now die, and we have y equals square root of 9 minus x squared. Square both sides. Y squared is equal to 9 minus x squared. Y squared is equal to 9 minus x squared, and move x squared to the left, and there it is. It's a circle. Do a little bit of this mathematical gymnastics, and you got your equation for the circle. So now, in general, I can write this in red. That don't have to be this dramatic, but circle is going to be x equals r cosine t, y equals r sine t as a set, where t is the parameter between 0 and 2 pi for the full oscillation, so you have a full circle. Ellipse is going to be x equals a cosine t, y equals b sine t, because it has two different values to make an ellipse. So these are the ones that are not obvious. Yes.
How would you backtrack? So like we simplified these problems to get the equation for a circle. Like how did they go from the equation of a circle?
This is the reason why I gave you to remember them.
Okay.
But for these, they're not unique. That you cannot have a mathematical procedure for something that is not unique. So you play with it and you get it. So here is a Calculus 3 question. I mean, not the Calculus 3 question. Calculus 3 question is to compute the line integral. But they say calculate the line integral for the line segment that it's going from 0, 0 to 5, 5. I can actually go into Calc 3 and find that exact problem. I did it last semester. We're not going to do a line integral. We are just going to do the line segment, which is parametrization, which belongs in this lecture. So, what what are the parametric, okay, not Parmesan cheese, but parametric equations? You say chicken parm? No, parametric equation, parm equations. Right here, come here. Parametric equations of a line segment from 0, 0 to, let's say, 5, 5. Okay. So I need a parametric equation set to describe a line segment which is the straight line. Now, do we all know that y equal mx plus b is the linear line? Great. Do we all agree that the slope in this case is 1 and the y-intercept is 0? Good. So the line segment going from 0, 0 to 5, 5 guys, right now this is your problem. In Calc 3, this is the calculation you do on a side in 27 seconds, so you can actually do the Calc 3 problem. So
we shouldn't take it over.
Learn it. No, you should. So what you have here is the equation y equal x. And your x is stuck between 0 and 5. Is this a parametric equation? No. It's not a parametric equation. This is your regular equation that you all know and love, right? This is y equal mx plus b. Your m is 1 and your b is 0, so you plug those in and you get this. Now we write parametric set. This is your parametric set. So if you make x equal to t, then your y is also equal to t, and t is stuck between 0 and 5. Easy peasy. So this is a part of actual problem that is there on your homework in a textbook for Calc 3, all the way in chapter 17 or whatever, but yeah. So parametric equations are going to break your dimensions, give a dimension x its own equation, dimension y its own equation. In Calc 3, there will be a dimension z with its own equation. And then we are going to write those three in a vector, which will point to stuff. That's Calc 3. So it's extremely easy. Right now, this is new because you haven't seen parametric equations before. You never broke your dimensions apart. But it is extremely straightforward once you spend 10 minutes on it.
So, how do you know what goes to what dimension? Can you make y different, or multiple equations do the same thing?
Well, I'm just going. Yeah, you have multiple ways. So let's go with the graph parametric set x equals t plus 1. Y equals t squared minus 2.
Is this a new problem?
Yes.
Okay.
I want to graph it.
I don't know. I'm so lost. I'm just trying to write stuff down.
So now I just want to graph parametric equation. That's all I want to do. Graphing parametric equation is going to take you back to your middle school era, where you pick your t's and you calculate your x's and you calculate your y's because you have equations. Then you will have x comma y points to plot and then connect the dots.
Couldn't you also change?
Now you're
Couldn't you also solve for t? No, solve for x on the top and plug that in.
yes, we'll eventually do that. So now parameter t. Parameter t can be regarded as time, and we can start our clock at 0 and then go through 1 second, 2 seconds, 3 seconds, 4 seconds just to see where we end up in life. So 0 for x, you see that x is equal to t plus 1, so all of these are just going to be plus 1. So 1, 2, 3, 4, 5, right? Now, y is slightly more annoying to calculate because you have to square. 0 squared minus 2, that's a negative 2. 1 squared is 1 minus is negative 1. 2 squared is 4, so that's a 2. 3 squared is 9, minus 2 is 7. And 4 squared is 16, minus 2 is 14. What I have here are 5 points that I can put on the graph, on a grid, and just connect them into a graph. So let's see. I need all the way up to 14. I'll call this 14. So time to graph. X is 1, y is negative 2. And that's my first point at time. Right? These are my x and y axes, guys. We don't have a new graph. We use the time parameter t to use that t in these equations to compute x and a y. And now you just have your good old 1 and negative 2 point. And you just graph them. The next one is 2, negative 1. 2, negative 1. The next one is 3, 2. 3, 2. The next one is 4, 7. 4, 7. And the final one is 5, 14. So you get this. Does this look like a parabola? It does, right? Now, I'm going to put something over here, which are these arrows going up like this. And I will call this a red arrow orientation. The time went from 0 to 4 seconds as a parameter. This graph was constructed from the first point 1 and negative 2 on the bottom going up. Therefore, orientation of this graph is the red arrows growing and going up. And that's the orientation of the graph. Why do we have an extra piece of information? Well, don't you have an extra degree of freedom, which is a t? When you just have x equals y squared, y equals x squared, you don't have anything past those 2 dimensions. So the only thing you can do is to draw the parabola and walk away. There is no which way the graph goes because you only have 2 degrees of freedom, x and a y, and you use them up to draw a 2D graph. Now, you still have a 2D graph, but you also have parameter t. Parameter t is time, right, which grows, and that will give our graph orientation. Now, before I go back to a circle, I just have to, real quick, over here, what Mike suggested, combine these 2 equations and verify that I am in fact getting the polynomial. So t is equal to x minus 1 y equals to x minus 1 minus 2 squared, squared. So this is x squared minus 2x plus 1 minus 2, and I get x squared minus 2x minus 1. So my function is this. So now let's calculate y at 1. What do I get? I get 1 squared minus 2 times 1 minus 1, which is 1 minus 2 minus 1, which is negative 2. That's this point. Calculate at x equals to 2. So y of 2 is 2 squared minus 2 times 2 minus 1. That's 4 minus 1 equals to negative 1. There it is, 2 negative 1. These two equations are the same equation. They just look different, right? Same you, different shirt on a different day. No, it's in the growth of t. That's why there is a next example to address exactly what you're asking. Going back to circle, parametric equation x equals r cosine t and y equal r sine t will be a graph of a circle of radius r with a counterclockwise orientation. Yes, x equal r sine t, y equal r cosine t as a parametric set is the same circle, except now orientation is the other way. We can easily prove this by plugging in a point. So let's use point t equal 0. I don't need to be dramatic. T equals 0 for the top example. So if t is equal to 0, I have x equals r cosine 0, which is r, and y equal r sine 0, which is 0. So for time t equals 0, I have r 0. X coordinate is r, y coordinate is 0. Well, that's here. So this is your t equals 0 point. For t equals pi over 2, your x is r cosine pi over 2, which is 0, because cosine of pi over 2 is 0. Y equal r sine of pi over 2 is 1, so it's r, and I have 0 r. That's the top over here, and you know that's t equal pi over 2 because it's all the way on top. So you see that you went from time t equals 0 to time t equal pi over 2, which is about 1.5 seconds later, or 1.5 hours later, I don't care. And you see that the first point was that one, the second point was that one, so you see that the motion is counterclockwise. Completely opposite story on the bottom. For t equals 0, starting point, you have your x equal r sine 0, which is 0. And y equal r cosine 0, which is r. Your first point is 0, r. You are starting over here on top as t equals 0. You just have to follow math, right? You're not memorizing anything here. And if t is pi over 2, your x is r sine pi over 2, which is r, and your y is r cosine pi over 2, which is 0. So now you have r0, which is this point. So at this point, I hope it makes sense to see that orientation is split, because first point being here, and then you go to the next one, then it will go here. If you keep calculating t equals pi, t equals 3 pi over 2, right, you will see that you are going counterclockwise. On this picture, when I have cosine and sine swapped, the orientation is clockwise orientation. The first point ended up being on top over here, and then the next point is there. So you see that the motion went this way. So now it's clockwise. So swapping sine and cosine swaps the orientation, but keeps the same picture. It's still the same circle with the same radius. And if you're not talking orientation, there is no difference which one you put first, sine or cosine. But in Calculus 3, it will be important which way orientation is for certain calculations, so you need to know it.
So you can just add, like, continue adding parameters to this graph when you add variables?
Well, you are just adding that the t is going to be pi and pi, right? You're calculating.
But I mean, essentially, like, you can have, like, as many variables as you want. They're all
yes. Yes, 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 yes.
Things about this graph. Okay. So it gets
Hence, the lecture in Calc 3 is not a chain rule, it's chain rules, plural, because it will depend on how many independent variables you have. So everything can depend only on a parameter t, but it could also depend on parameter r and t, or rs and t, or rs, t, and w. So the chain rule formula will change every time you have a different number of parameters. And the number of parameters determines the degrees of freedom in the dimensional space you're in.
What would be like an application for this? Where would you...
Well, easier calculations, and first off, it's not as easy to compute in x squared plus y squared equals 9, where it's much easier to compute 3 cosine t, right? The other good thing is it's time dependent. So you want to program something, right? You want to program something, right? That things develop in time. So you are tracing. It's much easier to trace velocity, to trace acceleration, to trace all of these things, because now I actually have, if I go back over here to this graph, I actually have a visual path for the bug to walk along this parabola. Let me find the velocity. Let me find it by simple derivatives, but I actually see that the bug starts here and it's walking this way because I have orientation now. So, and all of this, the question you were asking is a Calc 3 question. There is a whole lecture, a section, right, in a chapter, one lecture, on what you asked. And we're going to wrap that into a vector, and you will be able to determine and describe a spiral in 3D, and you will have a equation for that spiral. So if you have, let's say, an airplane doing the loops, right, for the, like, Carnival or whatever is the, right, and you see them do the loops and they let that smoke, color smoke out, right, they make the helix, right, motion as they go round, right, and they make the spiral like a spring. There is an equation for that, and parametric equations are the only way to describe these equations in 3D. You cannot come up with a single equation. So every single path in three-dimensional space will be broken with these things. We are just introducing the idea now that your dimensions can be broken apart, and we are doing this on a completely pointless examples just to give the idea. When you hit the Calc 3, you're going to have a helix. Helix is going to be like a spring. You know what a spring is. Everyone knows a spring, right? So what is your spring? It's a circle that spirals up. So your first coordinate is 3 cosine, your second coordinate is 3 sine, and your z coordinate, depending on how fast it goes up, if it's a linear, it's gonna be your regular spring. You can put t squared, it's gonna, go faster. So, you know, the angle of that t you can adjust with a 1/2 t, 3/4 t, 2t, depending on how fast you want it to linearly grow. So you can calculate a lot of cool things with that stuff. Again, really pointless for 2D, unless you're dealing with a circle, which is not a function, and you break it into functions, right? But parametric equations, they always have nice functions, and it's a really, 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 really cool thing. It's x. Yes, there will be an equation that calculates your x, an equation that calculates your y. We put that in a vector, and you can find the location in space. So if I am able to describe a flight of a bird or a plane or a bug through the 3D space, then I can, right? It's used to create the VR gaming systems and to make 3D video games, right? All of those engines have these calculations built in, because the only way to describe motion in 3D is to actually pile up 3 of these parametric equations, and in respect to time, my arm is here, 1 second later it's here, right? And it took parabolic way, so now we have a parametric equation in space that shows. Oh yeah, I mean, most of the stuff you did in physics is 2D, because you don't have a Calc3 vector, right?
So, those vector graphs that you see, say, you know, a wave in water, that can all be symbolized using this?
Yes. All of it. So this is what's happening in this particular lecture. That's a 12-1. And I believe that we only need to do one more thing, and that is to understand that, guys, what we have here is some kind of curve in space. So we saw that you can write y = x squared, and we saw that you can do x equals t, y equals t squared as a parametric set. Would you agree that this one has a tangent line at 2? It does, right? That means that this one must have tangent line at 2 as well, which means derivatives. Derivatives are okay. Now, what is your derivative here? Well, your derivative is dy dx. That's your derivative. Now, can I have a derivative equivalent for this? Yes. The derivative equivalent for this is dy dt divided by dx dt, because if I cancel these two, all you get is dy dx, right? So to find the derivative, all you need to do is to differentiate each one of these equations separately. Now, what is the really facepalm way to lose points on a simplest question that you can possibly see on the test? To put this one on top, because it was listed first here. It's y over x, which means the bottom one goes on top, and the top one goes on the bottom.
You could really brain that.
Yeah, brain that, exactly. So this one will be your dx dt, and let me put it in blood. It goes on the bottom. Denominator. There you go. So that way. Hi. No, you can put the negative ones, but t doesn't have to be time. T you can also put instead of t, you can put theta as the angle, so that can be your input parameter. Parameters don't have to. Generally, we like to think of time because it's easiest for us to think of the position and then velocity acceleration. But you can have other things to be this. So now, what is my derivative? Dy dx is actually just dy dt divided by dx dt, and please make sure that you put dy dt in the numerator and dx dt in the denominator. So we don't have those issues as we go. Now they're also defining the arc length, but there is a lecture for that in Calc 3, so I'm not going to bother you. They are doing it twice. So I'm going to leave that part out from this lecture and just move to 10-2 polar coordinates, 12-2 polar coordinates right away. What do you need to know for parametric? Change your regular equation into parametric, change parametric into regular, be able to graph by just finding 4 or 5 points, and be able to take the derivative by dividing the two independent derivatives. So those are the 4 points of parametric equations. Now, mentally, also you need to know what they actually do and why, which is they break dimensions apart so that you can even take some relations that are not functions and make functions out of them, so we can turn our calculations into much easier and friendlier environment. So parametric equations are really cool, and they actually help us a lot. And you will see in Calc 3, they actually enable us to do stuff, because in 3D realm, the only way you can describe a path is through a set of 3 parametric equations. So they are really, really important and fundamental for existence of Calc 3.
So for the final, we need to be able to find the coordinates of what else?
That's graphing. That's number 3. Number 1, change parametric into your regular Cartesian coordinates. Okay. Change Cartesian into parametric, so back and forth. Number 3 is graph by figuring out few points, and number 4, derivatives. So technically, guys, most of the stuff that we're going to do now is just pre-calculus 2 at best. Like,
You don't remember that. We're in Calc 2 now.
I heard that argument before, and it doesn't fly, my friend.
It's true.
Are there really 10 dimensions?
More. There is as many dimensions as you need to describe the equations that hold the space together. So 12, 13.
Yeah, I don't know. I just looked it up now. They're saying that there's like, length, height, depth, time.
So those are the 4. When you call space-time, those are the 4 that you mentioned.
Yeah,
that's space-time.
That's like what we know, and then there's like scientists say there's more. Like there's multiverses. There's like dimensions where like the Earth is like almost the same. Like we're the same, but we're kind of different. Like.
Welcome to physics.
It makes you like your brain.
Which is why you have 7 people working on it.
I love it.
Yep.
But I hate the math. I just like the concept of it.
That's good enough. Read it.
Yeah.
Read up. Polar coordinates. So I'm going to start this with a joke that is not going to sit with anyone. I really need you to wrap your mind around this. And it means nothing for you, actually meant for you, because you know what they are. So, polar coordinates. Your regular XY grid coordinate system that you are used to, and the most likely only one you know, is at 90 degrees. Look at your ceiling. I should be. Yep. So, when you look at the ceiling in this classroom, you see an XY grid. If you look at my screen over here, maybe you see the XY grid, the little squares, right? You are used to that stuff. You are used to reaching the point, let's say 4, 2, by going 4 units on x-axis because your x is 4. And then when you reach 4, you go up 2 units as y, and you reach your destination 4, 2. And this is what you have done since the dawn of your time, right? But now we are going to twist this a little bit. We are not going to reach a point 4, 2 this way anymore. We need a different system. So this system is known as Cartesian coordinates or rectangular, the one you know. What I want to do is I want to go with the polar coordinate system. I'll just put over here rectangular coordinates, and I'll just put old, meaning this is what you know, this is what you have been using all the time. So what's the new stuff? Polar. Polar coordinates work in circles. You are getting radius r, and you are going to swing that angle theta. So this is your point in polar coordinates. Let's see an example. 3 pi over 3. Now, I really need you to look at this. Forget about writing, because you can catch up with writing or you can get the notes. If you don't see this, it's just gonna go away and you can kiss some of the chapters goodbye in your Calc 3. I need you to understand this. I'm going to draw my regular XY coordinate system, and this is the way you find your 3 pi over 3. The first thing you are going to do is you are going to go out to positive 3 on the x-axis. That's your first order of business, is to graph your either positive or a negative r on positive or negative x. So that's first. Then you are going to determine where is your angle pi over 3, which is 60 degrees, so we'll say that's somewhere over here. So that's pi over 3 angle. Then you are going to take compass. You're going to put one end here, and then you're going to draw the arc of the length 3 and intersect the angle, and the point you get is going to be your 3 pi over 3. So the way the polar coordinates work is draw the radius, swing the angle positive, swing the angle negative. Or draw the negative, hold on, no. For you, this is positive. Reset. Draw the positive angle on the positive x-axis, positive angles up, negative angles down, right? For you again, negative axis is on this side, positive angles down, negative angles up. Negative angles clockwise, positive angles, the same like in pre-calc 2. Positive angles counterclockwise, negative angles clockwise. Basic trig, yeah. But you haven't used this coordinate system in trig, right? Well, What is the point? Go. You draw this. What is the point? Negative 4 pi over 4.
Kevin, you're sitting up front. She's a businesswoman holding a tail. Kevin, you're sitting up front. You didn't know that? Oh my God, I'm paying the wrong person. Oh my God. Okay, forget that negotiation. I'll find somebody else.
So we go and we draw 1, 2, 3. We go out negative 4. Pi over 4 is a 45-degree swing, and there it is.
Why did you go down?
Its positive angles go this way. It's a positive pi over 4.
So you're starting at that axis on the third.
You start, yes. Yes.
That's a negative y coordinate, though.
These are not x and y over here. These are r and theta. They have nothing to do with.
Okay then. This room. It's a Thursday.
Yeah, if it's Thursday, it's here. Is it Thursday?
Yeah.
Then we're here.
Same time.
Is it 5:30 or 5? 5:30 to 7:30.
Thursday next week? Nice. All right.
How did you figure out this right there, though?
I had a 45-degree angle, which I erased.
Why is it in the third quadrant, or whatever quadrant that is?
That's the third, yep.
Because you have a positive angle, but you're going in the negative direction. So if you're starting at the center, you have a positive pi over 4, so you're moving this way. But you have a negative magnitude, so it's in the negative direction. So if that 4 was positive, then it would be...
Then it would be here, and then you would go up.
What I like to do is I like to put almost in a pencil dead center, and this is your angle being positive. And then once you have your angle, you either move positive or negative on that line. So we're always going to be in either quadrant 1 or 3?
What happened?
So we will always be in either quadrant 1 or 3.
No, could be in any quadrant. Depends on how much I give you.
Depends on the number.
What does it look like if it's in quadrant 2 then?
Yeah. What would it look like?
Would they both be negative?
It would equate to over 90 degrees.
How would you?
Yeah, you can have both negative, sure. Negative 4, negative pi over 4 would be here. Because you go negative 4 and you go back. Because it was negative angle. You go clockwise. Try the one on the bottom. Someone eat this, please. I can't eat this. I've been eating all day. Every 15 minutes. All my classes have plus the party.
Is the magnitude of this length. The magnitude, if it's negative, or you're going to the right. If it's positive, it's 15 degrees.
No.
Oh. 15? Oh.
That's where you go.
No, it is. It's this thing.
What's the value?
Oh, it's -2.8.
That's fine.
That's the one for God that you use.
This one.
It's strict. And right the other way you use inverse strict to hit your angle.
Two dimensions still. That's boring.
No,
You know
you're
what I
gonna
saw?
go right
And
and now you're gonna go that way.
Clockwise, right?
But where does the negative 5
Didn't you just go counterclockwise?
30 degrees. A third of a.
You said clockwise. You just went counterclockwise.
But it's negative.
So you go clockwise.
Oh,
You got it.
Because you set this
Yeah.
up like a triangle here.
Where's my hammer?
You're going out.
I
You
don't
gave me
know.
this was a
He's in quadrants.
for this one. I used these 4 and 2 here.
When you
I'm going from normal coordinates.
Why don't you keep going to quadrant 3?
No, so when you, if it's a negative and it's counter, if you go into quadrant, it ends up this way, and it's going
So using only the
clockwise,
radius.
so this way, yeah, but if it ends up
You have the radius and you have the
if
magnitude.
he's this way, and you go the same way.
So he's drawing the triangle like this,
He
right?
ends up the opposite.
So if that was a 4,
Right triangle.
negative 3 pi over 4,
You know this, you
that
know the
would be the
hypotenuse,
third
and you know the
quadrant,
angle.
right? Yeah.
The hypotenuse.
I get this. Wait, is this
Your
going to be on
length.
the final?
Yes.
Okay,
This is where
now I
your point is.
understand this.
This is the center, and this is where your point is.
You just have to know the unit circle.
Point.
That's it.
You see what I'm saying?
I don't know why.
Well, I think he's doing 5 questions per each.
So this is like.
Just to clarify, your 4 is like your reference point. So like
4 is the radius.
Like if you have a protractor, you have like 30 degrees would be here.
Excellent.
But
Negative 30 is down.
since you're over here, it's negative. It's just down here.
So if you're negative 4, and then negative angle goes up. Negative 4 and negative angle.
Because negative is.
Negative is clockwise.
Oh, okay.
Positive is
This is the
counterclockwise.
radius, right? Now you're able to turn this in any direction, right? But you're able to change the length of the radius stays the same.
Ali.
That's how you're able to throw stuff. You know the angle, and you know how
This will
long
happen
the
in the
radius
first
is.
semester. After the first exam, he was just.
And then using trig, you can convert it from the Cartesian system to the.
So it was a 3 pi over 4.
Right, but if you have a circle,
And then the third quadrant.
This I definitely know, so I know the information.
4 was
That
the
is
minus
cardboard.
four.
I draw
Cardboard.
4 this way.
Yes.
So the 3 pi is down, right?
Because the 4 will go negative 4 over here and will go up.
So this is
Nice.
not going to be.
So
Take another one?
the second coordinate just tells you where on the unit circle you're getting.
Yes. How much you swing?
And the first number tells you left and right.
How much?
Well, it's about time. See, this makes sense. This isn't like secret.
So you have
The next one is now we do functions.
That is terrible idea.
So let's do the functions now. Now that you know.
break.
No.
Take 3.
Break. Functions. We'll do later. Yep. All right, guys. Time for functions.
What?
Apple juice kind
Yeah, I
of
want apple juice. That was
cotton mouth, huh? It's hitting you?
Yeah.
All right.
Pardon me, good sir.
He really is.
Good.
I'm switching my project up too.
You're given
This
Going
late?
for the lambda.
All right. So now
Good for
That's how you
you.
can go back and forth, and then the ball. Say you're given Cartesian.
functions.
Just helping myself right now.
Professor,
and use Pythagorean theorem.
It's public now.
Can you ask a question for me?
I'm gonna make
Anyone
a.
has an iPhone charger I can borrow?
This guy has.
She does?
Yeah.
He does?
Yeah.
Thank you.
Is that cream cheese?
No, it's cannoli filling.
All right, guys. So
You never had cannoli?
now that we are able to graph basic points
I'm about to change it right now.
Quietly.
in polar coordinates, so we know the way to locate basic point. Oh, hold on. Can't do this. I forgot to do something important.
Another section. You forgot another section.
No, I forgot to give you the conversion between two realms.
I just showed Mike that.
So we have we have your regular XY rectangular coordinates, which I call rectangular realm, and then you have the polar coordinates, the polar realm, right? What is the conversion from one system to another? So if you take a look at the way we find the point, right? And you understand which way you get it through both of these systems. This is your y, this is your x, this is your r, this is your theta. You use r and theta to get to the point using polar coordinates. You use x and a y to reach the point using rectangular coordinates. So, what is the connection between the two worlds? Well, if you take a look at this, you would definitely see x squared plus y squared equal r squared, Pythagorean theorem. And you see that if you solve this for r, you get r equals square root of x squared plus y squared. So if I give you x and a y, you can compute r. This belongs to conversion from rectangular into polar because you are getting polar answer given the input of two rectangular coordinates. The other one that you can write is the tangent of theta as y over x, from where theta is equal to inverse tangent of y over x. So I am able to calculate r and I am able to calculate theta given x and y if I use these two equations. And this is the conversion from rectangular into polar, because if you give me both x and a y, that means I have rectangular. I can calculate polar coordinates one at a time.
You want to make this the whole time?
I can also write sine theta is equal to y over x, y over r, and I can write cosine theta as x over r. So from these two equations, I can come up with x equal r cosine theta and y is r sine theta. This is the way to convert from polar into rectangular. Polar to rectangular coordinates. And I will ask you to hold off on a question. If we are converting between these two systems, why bother with all of them if our previous system worked just fine of xy? Hold off on that question, because I need to talk about functions first. But just by writing basic 4 equations for the right triangle, sine, cosine, tangent, and the Pythagorean theorem, you get all 4 equations to convert between the two systems. Now we are ready to talk functions. This is still 10-2. functions in polar coordinates are given as r equals f of theta. So theta is your input domain, r is your output, like a range. So functions are defined in this way. You know that for your xy coordinates, right, you have that y is equal to f of x. So this should not be new to you at all. Shouldn't be new. The y was the output, x was the input. Now, theta is the input, r is the output. Great. Looking at your basic rectangular coordinates, we had the basic functions where you just said, what do I get if I say x equals a number? What is this equation? What does this equation give you if you just take x equals a number? What is this? So y can take on any value. X is fixed to be a. What do we get? Vertical line at a. So the basic function in your rectangular, when x is equal to a, is just a vertical line through a. Now how about if y is equal to b? The other coordinate, right? Y equals b. What do I get? Horizontal line through b. Nice. So these are your very basic functions. Well, x equals a is not a function, but for rectangular coordinates. You have x equals a, y equals b. They're both straight lines through a and b, and that's the cheapest you can get. The cheapest, easiest you can get. Now, x equals y is already harder than this, right? And it's a 45-degree line. So what is the cheapest we can get with polar coordinates? Well, clearly, theta equals a number is one of the cheapest. So theta equals a. Let's say theta equals pi over 3. So what would that be? What is theta equals pi over 3? If you graph 60-degree line. It's the infinite linear straight line through origin at 60 degrees. So if theta equals a, you are getting some line at the angle a that it's infinite and it goes through the origin. That's what you're getting as a basic function, theta equals a. What do you get for r equals a as a basic function? Now, this is the one that defines life over here. Well, think about it. Your r is set to be, let's say, 3. Your theta is allowed to take all values. What do you get? Circle. Clock. Because your minute hand, it has length, right? And here's the top of the minute hand. It's going to take all of the values as it goes around, because remember, you can take all the angles. 1 degree, 2 degrees, 3 degrees, 4 degrees, 5 degrees, 6 degrees, 7 degrees, 8 degrees, right? And it goes like this all the way around 360 degrees. Then it goes again around because the day continues, right? 360 degrees to go through the first 12 hours. I mean, first hour, right? And you keep...
And if you look at it, when you're spinning really fast, it looks like a circle.
Yeah, so that's it.
Essentially what you're doing. But
Because you stretch your radius A over here, and then you just give it all the values.
exactly.
We can do the experiment.
So are they always going to be circles then? Well, assuming your A doesn't change. Okay.
If your A is a constant number, if you start changing A, you get a spiral. With a right, if the A is growing, it spirals out. If the A is getting smaller, it spirals in until A gets to 0 and it hits the origin.
So this kind of makes sense.
Yeah, it's math.
Yeah.
So
It's not sequences or theory. It's also math. That's not math. That's aliens.
So hold on, guys.
Wait a minute. This is something that we learned in physics where it's like you circle around like a bunch of times. I forget what it's called, but it's like some kind you have to calculate it's like in radians or something.
Yeah, we'll do this in radians.
Times it goes around like to calculate
Reference angles and reference, yeah.
it goes around. Is that's like,
No, we're not going to use that here, but yeah, it can be used.
I forget what it's called. A lot of this stuff is in physics. Like all of this stuff.
It's basics for it. So here we get to the most interesting part. Can you realize, guys, that the basic function for polar coordinates is a circle, right? What do you have to do? What do you have to do? How much do you have to suffer to differentiate and integrate circle in Cartesian rectangular coordinates? Differentiation, implicit differentiation, not fun. B, integration, can't do it. Or you can, but good luck, you have to mess with trig sub, right? Yeah, trig sub. So, not fun to differentiate or integrate in the form of x squared plus y squared equals to r squared. But now, your equation for a circle that used to be x squared plus y squared is equal to, let's say, 16 in rectangular coordinates is now r equals to 4 in polar coordinates. Woohoo! So polar coordinates make a joke out of these circular kind of things and motions.
So wait, if you integrate that, you get 4x, say, and then you convert it back to
Not 4x.
I mean, 4r.
Yeah, you have to. Yeah, we'll talk about. We're getting there. So hold on. So this is the part where I can answer your question. Why bother with a new system if the old one worked just fine? Well, it didn't work just fine for circles. Now it's going to work insanely fine when I just have that the entire circle can be described as r equals to 4, right? I don't have x squared, I don't have y squared, none of that stuff, everything gone. All I have is r equals to 4. So all of a sudden, all of the calculus becomes a joke, right? So now, is this a competition or opposition of these two? And the answer is hell no. These two systems complement each other. What's beautiful and easy in the rectangular coordinates, your squares, your triangles, your rectangles, all of those, and integration and differentiation of all of those, and including the x squared and stuff, right? That all stays in your regular coordinates realm, because everything you want to do about it and you know about it is easy. Then you run into a circle. Circle is not a function. Immediately it becomes nasty calculation for derivative, nasty calculation for integration, and just not great. Switching into a polar coordinates, you are making a joke out of that. So these two systems don't compete. they work together, and certain things are easy to describe in polar coordinates, and other things are absolutely terrible to describe in polar coordinates, and you should use rectangular coordinates. Now, polar coordinates in Calculus 3 will give rise to two different coordinate systems for 3D. Both cylindrical coordinates and spherical coordinates will have polar coordinates as a 2D base. And then you are building the 3D on top of it using either Z or using another angle phi. That's for Calc 3. But you have to understand that the third-dimensional coordinate systems, you have one that is built off of the XY, which is XYZ, which is the rectangular system to get the box, like the box we're sitting in. But if you want to deal with a sphere, ball, right, you will have to use spherical coordinates. If you want to deal with a cylinder, like the soda can or this cup, you want to use the cylindrical coordinates. And those are built on polar coordinates because we see a circle on the bottom, right? And the ball has the circle at the equator. So these coordinates are going to give us more stuff when we go to Calc 3, right? So you can't ignore this. I mean, if you're not going to Calc 3, then yeah, sure, right? But going into Calc 3, this is going to give you entire, chapters worth of stuff to build up on. So you gotta know these things. Now, the next one is, can your TI 8384 calculator, can your calculator graph these polar graphs? And the answer is yes. If you have a calculator, now is a good time. If you have appropriate technology, it's a good time to get the app. It's free.
If I would have known that was free, I would have never bought.
I know. The
Yeah.
school screws
They're
you
so
like that, right?
expensive.
Oh yeah, you need a graphing calculator for pre-calc
Yeah,
1
and
and
you
2.
don't even
But then
use
you're
it.
not allowed to use it ever again.
Yeah, exactly. It's like, what's the point?
Ready? We are going to push the mode button to make sure that we are in radians. Otherwise, your calculator is going to explode. Then, on the line 4 under mode, says Funspar pole sequences, right? You're going to go to pole, P-O-L, polar. So you have to switch your calculator into polar mode. And as you can see, there is a par mode, which is parametric equations. This can graph parametric equations as well. And it can graph your sequences in series. That's what the sequence is at the end. I'm trying to get this thing to work. Document orientation and full screen. Great. No, don't do that. Hey.
Upside
Upside
down.
down.
Is it?
Yeah.
How do you know?
Because it looks like
Oh, he's good.
Of course I'm good. Oh, come on. Trying to get it to get. Oh, it's actually the phone is. You want to go there again? Like, you really didn't learn anything last time? All right, so here we go. Now, so mode, you will switch over here in the fourth line to POL, stands for polar. Now, we're going to go second quit. We're going to push Y, and when you go to the Y screen is going to give you all of these R's instead of F's. Earlier you had F1, F2, F3, now you have R1. Type in 4, sine, let's go with 4. And now when you push the variable x, you see that it says x, t, theta. T is for parametric equations, and theta is for polar, so you push that, it will print theta. And you close parenthesis, push enter. Now, before you graph, we're gonna go into window. Go to window and set your x minimum to -6 because I want this to be nice. So go here. Oh, this is supposed to be 2 pi. Hold on, I messed this up. So just go to the x minimum and put -6. Go to the x max, put the 6. Go to the y minimum, put -4. And go to the y max and put +4. And now push graph. You get a flower. Now, if you want middle of the flower, go back to y equal. Go to the next line, and put maybe 0.5 sine, and then put maybe 20 theta, and that's going to be very busy. And hit graph, and then you're going to get this middle filled in. So now it looks like a better flower. So can you do this with x and a y? No. Okay? No, you can't. Because equations would be absolutely insane. Absolutely insane. So this is what you do. Now, what you can understand after this lecture is when I am the PC now. So if I go here into the, I say, heart, equations, math, images. All right. Let's go with this image here. Oh, come on. That's terrible.
Yeah.
Oh, much better. Still not great, but look at this. This object over here is called the cardio, heart, and it's r equals 1 minus sine theta. That's your polar curve, and it gives this not as nice heart shape, but it's okay to some extent. Your parametric equations can give this type of a heart. The two nicest hearts over here, this one is the polar heart with a little bit complicated equation, but if you are to type this in, you're going to get this heart. And then here is another parametric heart that you can graph on the calculator, right? So you are using equations, right? You haven't dealt with these equations before, but you can come up with curves, and clearly you can graph much more stuff now than just x squared and x cubed and sine x, because now the shapes become. Now obviously you need to explore and work on these things to make this stuff make sense. Now if I go and assign my equation as, let's say, r equals 1 minus sine theta. 1 minus sine theta, which gives me this cardioid like this. And that's on XY graph. What is the equivalent equation in XY realm? Well, one thing that I can guarantee is going to be disgusting. What is R given as? It is given as the square root of x squared plus y squared. 1 minus, and sine theta can be given as y over r. So let's do that, y over r. And now you still have to change the r. So square root of x squared plus y squared is equal to 1 minus y over square root of x squared plus y squared. Now you multiply the entire equation by the square root of x squared plus y squared to kill the denominator. Well, that kills the other side as well, which is nice, the square root. You do get the square root over here. And then you have minus y. Do you get to solve this as a y equals something? No, you don't, right? So this beautiful simple equation here spawns this monster in rectangular coordinates. This is why these two systems do not compete in any way. They do not compete. They complement each other. Your rectangular system is strong in one area of existence in mathematics. The polar covers the other side, right? So we don't want this stuff. We want to understand it in its pure form, when it's easy for us to say, if theta is equal to 0, what is my r? If theta is equal to pi over 2, what is my r? And you will be getting these points along the line to graph each one of them, and you connect them, and it creates the shape. So if I want to graph a polar graph, I will, so let's say I have y equal 1 minus sine theta. I will do the middle school approach. Theta equals 0, theta equal pi over 4, theta equal pi over 2, let's say. So let's just do those three. And then you are, not y, r equals. Yeah. So now you calculate your r's. You plug in 0 into theta, and your sine of 0 is 0. So you got your 1 minus 0, which is 1. You plug in your pi over 4, you get 1 minus root 2 over 2. You plug in pi over 2, you get 0. So now on the graph, you have your r comma thetas, and you start graphing. When your r is 1 and the angle is 0, that's a point. Because angle is 0, it doesn't move from the x-axis. 1 minus square root of 2 over 2, so this is about 0.3. And it needs to go to the pi over 4, so it's going to be somewhere over here. And then the next one is pi over 2, radius is 0, so that's origin. What you see with these 3 points that we got, so this is your theta is 0. This point over here is your theta is pi over 4. And this point over here is your theta is pi over 2. You connect them, and you see this portion of the graph completed. So it's really Right? So you get that, then you go to the other side, then it goes down and comes back full circle as you go through 2 pi.
So for the final, you're going to give us a function, and then we need to graph it like that.
Sure. Why not?
Some weird shape we have to figure out.
There are no weird shapes.
Yeah, I mean, like, you can make like a heart. We have to figure out.
There's a heart, there's flower, there is circle. It's not.
Oh wait, that shore wasn't very convincing. So I need to know, do I need to study this?
I thought you registered for the class.
No. I don't know anymore, man.
You don't know speaking.
I don't know. I'm just trying to hold on to my sanity. I'll have to use your animal from
Do that to me.
I would like to one down.
I'm not taking animal inside. I have decided.
I'm already
The
stressed
only way
out.
that I'm taking one of the time is to fail the class and take it again.
So what are these math?
Yes.
I know a little bit. The way you had R equals 1 minus I theta. You explain how to turn the square root of 1 squared plus 1.
You mean this? Those are the conversions that we had here.
No, like this is easy, right?
Oh, okay. So, yeah.
Green? Good. So I just use the conversions to convert everything so that there are no more r's and thetas, and try to simplify it, but you never get to go far.
Converted it from polar to rectangular?
Yes, just to show that it's going to be absolute horror. Completely useless. Completely useless. That was the only, the only reason why I did this is just to show that it's completely useless to convert one system into another, because they each is strong in its own. Now, you guys will be converting these systems in Calc 3 because you will get an integral of some kind that you don't want to work on, right? And if you transfer it into something else, it becomes so.
So how do you integrate that circle that you were saying?
Well, this is the beautiful thing. Look, if you have an integral of e to the square root of x squared plus y squared, right? Well, this is e to the r when you transfer it, right? Look at this monstrosity, right? But it's just e to the r when you convert it.
I read that.
Wait, if you change it to R, what would if you're integrating that, what would your D variable be?
There is dx, dy, there is r, dr, d theta. There is more stuff, okay?
Right.
Don't worry about Calc 3 stuff. I'm just worrying about conversion between the because that's where we are at. I don't want to teach Calc 3 now because there is no need, right? I'm just saying, if you have the integral of something terrible, right, you just go down and it becomes, oh, look at this. Because I know that the integral of e to the r is e to the r. Woohoo!
If you get me going, or see how the rest is.
Calc 3.
I know that.
And it's, what? It's 2 weeks from now.
There's no need to change.
Calc 3. In 2 weeks it starts. If you're interested in this.
So wait, I'm going to say it in your terms. So there's no way to mathematically, or no need to mathematically decide the function that you use, right?
Exactly.
You're just giving us a function and we're graphing it.
You want to graph it.
Okay. What made you choose pi over 4 and pi over 10?
Those are the values that I can easily calculate. Choose pi over 6, pi over 3. Those are the values that, right here. Remember the
3 pi over 4, all that stuff.
the pi over, this is pi over 3 or pi over 6?
Pi over 4, pi over 3.
I'm not sure which one was this. Pi over 4?
Pi over 4.
Oh, pi over 4.
You know that you're straight up.
This correlates with this. This correlates with this.
He's seen that.
So it just means it's congruent.
So yeah.
All right.
You know what you would better?
So, how about we do one more thing, and then call it a night, and then we do the review. So, I mean, call it the course, because there is no more lecturing.
Kevin thought this whole class was the review, so you've already got him all screwed up.
So basically, we're gonna have 30 minutes for.
Yeah, we don't need that much. Maybe 15. It's good enough.
I mean, you should know it already. To be honest, we all know everything except for sequence
So, guys, 10.3, 12.3 used to be 10.
Yeah.
Calc in polar coordinates. We got this. So we have some functions in space, and those functions have tangent lines, and those functions are cutting the areas off, which means we should be able to calculate derivatives to find tangent lines. We should be able to calculate integrals, to calculate areas. All of that good stuff remains. I don't have time to derive this formula, so I'm just going to write the dy dx for tangent lines represented through polar coordinates, which is f of theta for r and then just theta. This would be f prime of theta sine theta plus f of theta cosine theta divided by f prime theta cosine theta minus f of theta sine theta. Why is this derivative so insane? Because I'm trying to find dy dx rectangular derivative off of the polar functions. Of course it's going to be disgusting. It has to. So this is a derivative to find, this is the way to find the derivative for tangent lines using polar coordinates. Now, the one that you actually need to know is integration, because the integral now is given, right? It's going to calculate the areas, and you want to calculate areas for like, let's say you want to calculate the area inside the cardioid, you want to calculate the area of the circle, you want to calculate the area of the flower thing, you can. Area is given as 1/2 integral alpha to beta, these are now angles, of f of theta squared d theta. So, before you run, what happened? Beta. It's a Greek B.
I thought theta was the...
Theta is theta. Beta is beta. Theta, beta.
Oh, you said beta.
Yeah, beta is here.
Oh, I thought you said beta.
See, everybody's confused.
No, well, that would make sense.
What's the fish?
What fish? Oh, alpha.
Oh, okay, gotcha.
It's just a regular fish, guys.
Oh, the fish in the bottom is what?
Salmon. I know.
Alpha.
That's alpha. Yeah, it looks so.
Area is two-dimensional. I already have 2 dimensions here. Times d theta. Okay. Theta is not a dimension, because theta is in radians, and radians is actually the unitless unit. It's not a length. right? If you know the arc length formula S is r times theta. So theta is S divided by the radius r. If arc length is in, let's say, meters, and the radius is given in meters, when they cancel, theta has no unit. We do use radians, but it's a unit that it's actually a ratio. It's not a unit in terms of meters or inches or anything. So this actually doesn't bring a dimension to our calculation. Both dimensions are encoded in the square over here. So this is area. Okay, good. So dimensionally this equation makes sense. Now, what do you have to do to integrate area of the circle in rectangular coordinates? Holy nightmare. If you say x squared plus y squared is equal to, let's say, 16, you solve for y as a plus minus square root of 16 minus x squared. Then, to find the area, since this is plus minus, you're going to do only 1/2 and multiply by 2. Area of the circle is 2 times the integral of 16 minus x squared dx from -4 to +4. And then you have to do trig sub, right? Those are the limits on the circle, right? Because the radius is 4. It's 16, right? So radius is 4.
Okay.
So when you are integrating upper half, you have a function, and then from -4 to +4 on the ends, right?
Oh, and then you multiply this. I get it.
Yeah.
Okay.
So, living nightmare, right? Nightmare to set up, nightmare to calculate trig sub and all of these things, right? Let's take a look at the polar version of this. Polar version says the following. R equals to 4. Now we know that R is actually f of theta. So f of theta is 4. The full circle happens when theta goes from 0 to 2 pi, right? So, to find the area of the circle, I have 1/2 integral 0 to 2 pi of 4 squared d theta. This is how polar coordinates make a joke out of circles and things like that.
How did you get r equals 4 in that?
Well, what's the square root of 16? It's r squared, right? So now, this is 8 integral d theta, 0 to 2 pi, which is 8 theta, 0 to 2 pi, 16 pi. Go ahead and crank your trig sub and, right? So again, these systems do not compete because each one is so superior in their area, it's unbelievable. Now, how easy is to use rectangular coordinates to find the area under the triangle? Easy peasy, right? One-liner. You are just integrating linear line. That linear line in polar coordinates is a living nightmare. So something that is extremely easy to be done in rectangular coordinates, it's going to be nightmare in polar and vice versa, right? These systems do not compete. They're all kings of their own realm. So we're going to leave it here. I will see some of you over the summer. We will pick up in the summer for Calc 3 and just bring this further.
I thought he meant for count 2.
Hey, you never know.
No, I'm doing Calc 1 and Calc 3, so you better be signing up for Calc 3.
So good.
I don't want to do this again. Yeah, I hope to never see you again in Calc 2.
The field is neutral.
Yeah, we hope so.
Yeah.
In Calc.
So that's technically what we have, right? Yes. Oh, the formula was f of theta squared, right? And if your f of theta is 4, then 4 squared, right? Yes?
Going back to the derivative formula. Now, when we took the derivative, that would get us the derivative in Cartesian.
So you can do the tangent line because the lines are user-friendly in Cartesian, not in polar.
So you couldn't just take the derivative in polar and then convert that after.
Pick your poison.
Well, so would you say it would be easier to use the other method that we did in California? What was it called? Implicit differentiation?
Yeah, but usually you're given a polar equation because no one is going to give you the Cartesian equation. And if you have a Cartesian equation, look at it. For something that is as simple as 1 minus sine theta, you get that monstrosity, go ahead, do your implicit differentiation for it. Every y has to have dy dx. The square root is a chain rule with all of this stuff inside. It's a living nightmare.
Now, what about, can you convert the whole function from polar to...
That's what we did.
That's what, yeah, what am I saying? We did that.
That's what we did, and that's why it was bad.
Say they gave me a function in polar for that, and I convert it to linear, or I mean...
That's what I did, and it weren't bad.
No, it was bad.
That's what this is. I was given polar, and I went into Cartesian, and it was a living nightmare.
For this weird shape, okay.
Yeah, that's why I say. If you have a polar coordinates, stay with polar coordinates because they're nice. You have the Cartesian coordinates, you use the Cartesian stuff, right? The shape decides which one you use, not you. Shape.
Will this monstrous integral, will I have to memorize that for the final?
It's coming up in Calc 3. So. Yes. It's coming up in Calc 3.
So, my question
Let me just end this.
are you
Bye.
always going to have it from 0 to